Okay, so now we're going to look at some application problems. One of the most common applications for vectors is in physics when we're thinking about forces, okay? So forces are what make things move. So for example, if I were to drop this can of puffs, there would be a gravitational force, the force of acceleration due to gravity, that would make it fall down, okay? Now if I want to lift this can of puffs, well, I have to overcome that force. So there's a force going up, which is my lifting, and there's the force of gravity going down. In order for the puffs container to actually go up, the net force, that is, if I were to add the force going down with the force going up, has to be going up. That's what makes this puffs container go up. Okay, so we're often interested in the net forces on something. That is, if you take into account all of the forces or all of the vectors acting on something, what's the net force? So that's what we're going to look at with this particular example. Okay, so now let's look at an example. Piper and Max were both pulling on a toy as shown in this sweet diagram below. What is the net force on the toy, also known as the resultant on the toy? Okay, so in this picture we have Max pulling in this direction, okay? And he is pulling maybe with a vector that I represented as -2, 2. So he's pulling upwards in this direction. Piper is pulling downwards in this direction, so her vector might be 2, -1, okay? One thing to think about is with a vector, when we're representing them, so when we're representing forces in terms of vectors, is there's two main things, right? We can think about the direction of the force, okay, the direction of the force, and also the magnitude or the strength of the force. Now, that would be represented by the magnitude of the vector. So we could think about the magnitude of each of these vectors, and let's just go ahead and compute those just for fun. So the magnitude of Max's force, I would calculate as the square root of -2 squared plus 2 squared. So that's 4 plus 4, so this would be the square root of 8, which if I want to be good about it, I should remember that 8 is 4 times 2. So the square root of 8 is the square root of 4 times the square root of 2. So I get the magnitude of Max's force is 2 times the square root of 4. The magnitude of Piper's force, I could calculate as the square root of 2 squared plus -1 squared. 2 squared is 4, 1 squared is 1, so this is the square root of 5. Okay. Notice that means that Max's force is stronger than Piper's force, which makes sense because, at least for this problem, Max is stronger than Piper. Okay. Now, the resultant force, right, is going to represent kind of the net force on the toy. It's also going to tell us how the toy actually moves. And to get the net force of the resultant force, we just add together all of the forces that are acting on the toy. Now for this, we're neglecting the force of gravity, any kind of air friction or anything like that. We do that a lot in physics. So to get the resultant force, I would add -2 plus 2, which is 0. That says the toy is not going to be moving left or right, okay? And then 2 plus -1, which is 1. So that says that the toy is going to be moving upward because our resultant force only has a vertical component. It's not going to be moving left and right, only upward, okay? Let's look at another example. It's kind of weird, honestly, in this example to have our forces as a horizontal component and a vertical component. Most often when we're dealing with vectors, and not most often, but often when we're dealing with vectors, we're going to have our forces given to us in terms of an angle and a magnitude. So a strength of a force, as well as kind of the angle or direction of the force. All right, so Max and Piper are still pulling on the same toy, okay? Max is pulling with a force of 0.5 newtons. Newtons is the metric unit of force. Piper's pulling with a force of 0.25 newtons. Again, Max is stronger than Piper at this point. Piper's pulling the toy horizontally, and Max is pulling at a 105-degree angle away from her. What is the resultant force on the toy? Okay, so in order to do this, let's draw ourselves a little picture. Okay, so here's the toy, and I'm going to use vectors to show the force on the toy. So first of all, we have Piper who's pulling horizontally. So here is Piper's force. She's pulling in this direction, and what we know is that she's pulling with a force of 0.25 newtons. Okay, so 0.25, that's the magnitude of Piper's vector. Okay, now Max, it says, is pulling at a 105-degree angle away from her. So somewhere, here's Max, okay, and he's pulling with a force of 0.5 newtons. That's his force. Okay. And it says that he's pulling at a 105-degree angle away from her. So this is kind of what our picture looks like. Now what we want to know is we want to know the resultant vector. Okay. Well, there are a couple different ways to do this. Okay, and I'm going to show two different ways to do this. The first is we can take these vectors and we can break them down into their component parts. Okay? In other words, I can figure out the vertical and horizontal component of each of these vectors, and then I can add them together to get the resultant vector. Okay? Let's do that method first. So remember that when we're converting from, so if I have a vector that's given to me, so say vector v is given to me in terms of its magnitude, so this is the magnitude, and theta, the direction angle. Okay. Then to convert from a magnitude and a direction angle into horizontal and vertical components, so a horizontal, I'm not going to have enough room, and a vertical component, remember that that's going to look like the magnitude times cosine of theta, that's the horizontal component, and the magnitude times sine of theta, that's the vertical component. And that just comes from our right triangle trick. Okay? So if we want to use that, or maybe logic, to figure out the horizontal and vertical components of Piper's vector, well, if we use our formula here, it says we should take the magnitude of the vector, which is 0.25, times cosine of the direction angle. What's the direction angle for Piper's? Well, 0, right? The direction angle says the direction off the x-axis or off the horizontal. Piper's vector doesn't differ from the horizontal, so her direction angle would be 0. So I'd have 0.25 cosine of 0, 0.25 sine of 0, not theta. Okay? And let's see if we can figure out what that would be. Well, 0.25 cosine of theta. Cosine of theta is 1, so I have 0.25 times 1, so it would just be 0.25. Cosine of 0 is 1, sine of 0 is 0. 0 times who cares, it's 0. So this tells me that this vector only has a horizontal component. And that makes sense, like, right? Look at this vector. It's just horizontal. It doesn't have any vertical component, vertical up or vertical down. Okay? So now let's think about the vector that is Max's force. Okay? So the vector that is Max's force, well, it has a magnitude of 0.5 and it has a direction angle of 105 because we've literally said this angle from the horizontal is 105. So that means that the components of Max's vector, here's Max right now, he's waving at you, are going to be 0.5. You need to wait just a minute, buddy, okay? Cosine of 105, that'll be our horizontal component, and 0.5 sine of 105, that will be our vertical component. I'm going to pause real quick and take care of this kid. All right. So we were trying to find the components of Max's vector. I'm going to go ahead and just do a decimal approximation. I made sure that my calculator is in degrees, and I'm going to do 0.5 cosine of 105, which is negative 0.13. So negative 0.13, and then 0.5 sine of 105, which is 0.48. Okay. All right. So now that I have the components of these two vectors, to figure out the net force or the resultant, I can just add those together. Okay. So I'm going to add negative 0.13 and 0.25. So 0.25 minus 0.13, which is 0.12. And then 0.48 plus 0, which is 0.48. And that gives me the resultant vector. And if I want to sketch that in a little bit, right, what is that going to look like? It means the toy is going to do something like move something like this. Okay? So that's another way to think about force problems. Oftentimes when we have a force problem, we're given the strength of the force and its direction, and then the strength of a force and its direction, or we're given the strength of two forces and we're given the angle in between them. Okay? we're gonna look at one more example, kind of the most general sort of example that we'll see of these application problems. Okay, sorry, I know that I usually say sketching is sketching, but even I couldn't handle that. So just as a reminder, we have a 40 Newton force this way, a 25 Newton force this way. The angle between them is 100 degrees, and we're looking for the resultant. We're looking for this vector right in here. And really, we just want to know the magnitude, okay, the magnitude of that vector there, okay? So how can we do this? Well, the way that we can do this is to remember that in this parallelogram, right, the length of this side is also 25, and the length of this side is also 40, okay? And then I want to see if we can figure out the measure of kind of all of the angles of our parallelogram. Well, this angle has to also be 100 degrees, right? 100 and 100, and these two angles have to be equal. So what do we know about the total angles of a parallelogram? They sum to 360. They're two triangles, 180 and 180 is 360. We've used up 200 of that, so 360 minus 100 is 260, minus another 100 is 160, okay? So we have 160 degrees that is going to be split up between these two angles. That means each of these angles must be 80 degrees. Another fact that you may or may not remember or know is that neighboring angles of a quadrilateral are supplemental. 100 plus 80 is 180. Okay, so great, who cares? Why did we do that? Well, the reason we did that is because now we can look at kind of this triangle. Really, we can look at either triangle. I'm just picking this triangle here, okay? And now we can apply our law of cosines to figure out the length of this vector here, okay? So we want to know the length of this guy. I'm going to call, I think I already called it V earlier. We want to know the magnitude of V. So the magnitude of V, okay, by our law of sines, right? I can think of the magnitude of V squared. Remember what our law of sines says. We have three different versions of the law of sines. We have one that says C squared equals A squared plus B squared minus A B cosine of C, okay? So this is acting like my C. Either of these can be A and B, and then this is my angle C. So by law of cosines, V squared, the magnitude of this, is going to be equal to 25 squared plus 40 squared minus 25 times 40 times cosine of 80. Okay, so I'm going to go to my calculator, and I'm going to enter 25 squared plus 40 squared minus 25 times 40 times cosine of 80. And that gives me 2051.3. 2051.3. That equals my magnitude squared. So if I take a square root of that, taking the square, that one's no better. There we go. Taking the square root of that will give me the magnitude of that force vector, that vector V. So the square root of 25051 that's too many. 2051, got this. I get square root. 2051.3 is 45.3. So the magnitude of this vector is going to be 45.3. Okay? Again, that doesn't tell us anything about the direction of the vector, it just tells us the magnitude of that force vector.